No. Tak, dámy a páni, myslím si, že už sme dali dostatok času aj vašim kolegom, aby sa
Okay. So I have mentioned that with the next presentation, we will stay here in Slovakia, let's call it, and applied IT is really booming, and it is a very important segment also for today's conference, and that's why applied informatics. This is why I'm very happy that I can invite our next speaker on stage from a community. I mean, we have spent some time together. We have studied together. So she's from the Department of Applied Informatics, Faculty of Mathematics, Physics, and Informatics. Madam Kristina Malinovská with her presentation on AI and cognitive robotics. Yes, good morning. Mic is working fine. So this topic is very resonating in the society, and I am looking forward to your presentation, and let's enjoy it together. Thank you. I would start directly with some basic definitions, and I will stand here in front of my presentation. So cognitive science is a study of mind. I mean, has been mentioned very often also in connection to AI and with deep networks and its use. But I also want to underline that it is an interdisciplinary study of mind. And of course, one of the pillars is AI, but it is also philosophy, psychology, neuroscience, linguistics, and it includes all these kind of scientific fields, and we are trying to combine all of it and to create something new, something that is based. We are trying to create systems which are able to learn, so they have some so-called body, and they're interacting with the world and the humans, and they can contribute, they can help and assist us also in some industrial applications as well. I would like to introduce our working group. The name is Cognition and Neurocomputation Group. So we are investigating artificial neural networks, so deep learning, reinforcement learning, but also creating new neural networks and the basic research connected to it. We are also working on explainable AI, how to interpret these deep models that we are all using, but we not always understand what they mean. So we also deal with cognitive robotics. This is the central topic of my presentation, and it's a new part, which is called the human-robot interaction, HRI. We do have robotic platforms, so we have this small humanoid. It's called the Nico robot. I am covering it, the picture of it, but you will see it during my presentation. I will try my pointer. It's working. And the news is that we have these walking, almost humanoid robots, which are called Unit 3, and we are researching those. And I would like to mention also that we don't deal only with research, but we also with education. So we do have an international master field of study, which is mentioned here, and we also have a so-called Slovak organization of cognitive science. This is our group. So you see the faces, and I will speak now about our projects and partners. So these are a few selected ones. And I would like to pinpoint Horizon project now. So last calendar year, it was successfully concluded. Our international partners are mainly the Czech Technical Learning in Prague, then University of Hamburg, and the Italian Institute for Technology. We also have Slovak partners, for example, the Slovak Academy of Science or the University of Technology in Košice. So as for the projects, you see here the acronyms, the names of the project. So we deal mainly or focus on humanoid robotics and how to interact with people or with humans, either in some therapeutic implementation or how to interpret and explain those, and these towards excellent robotics through artificial intelligence at Slovakia University. So this project was our breakthrough project, because for the first time at our faculty it was were acknowledged this size of a project, so it's within the horizon scope, and it has made it possible for our scientists and basically all the staff at our chair. It was the possibility to learn about or from our international partners from Genoa, from Hamburg, and the budget was also quite nice. And it was not only about research or conducting research, but also about supporting the structures at our faculty and our chair. So it was also a career opportunity for our employees, and we also created a so-called research support unit. So it is quite a novelty also at our university. So what is cognitive robotics? What does it mean? So these humanoid robots, if we want to communicate with them, live with them, and use them, and somehow identify with them, they should have different skills or capacities that remind us of humans. So they are learning, or they are also interacting and leading conversations with us. So they need a special set of skills. So cognitive robot is very different from an industrial one. It's not that it cannot be used in the industry, but it means that we don't need to be as precise, but we need the robot to be sensitive and not to harm humans. And how we use cognitive robotics enables us also to find out more about ourselves. So we are using the knowledge from our interdisciplinary field of study, so cognitive topics, and we are having an insight into how the human mind and human brain work. So we do have this methodology. It's called understanding by building. So we are building to understand how we work. And this is what we need these humanoid robots for, and the platforms who resemble humans, basically, and we are using this methodology, and we also bring technology, including AI, which is then better explainable, more safe, and more predictable as for reactions also for end users and, well, humans. I have already mentioned it. So why should we, in our field, in interaction between humans and robots, I mean, of course, how are the smart systems designed, and why they should basically interact and cooperate on a daily basis, basically, and develop this methodology of cognitive robotics. So cognitive robotics basically predicts that the robot will develop and learn and study. And at the same time, I mean, we are not only finding out how to design robots, but also we are finding out how humans react to robots, and this gets us knowledge for improvement of the robots. So you see this in this loop. We are also trying to design a robot in a way not only to be able to explain why the robot acted as it did, and also that we understand the motivation or the reasoning. So just like when you communicate with ChatGPT, the ChatGPT responds like, why do you think this and that? ChatGPT tries to explain, and the robot should do the same, but in like a living context, communicating with you, acting, maybe gesturing, nodding, and so on. And we have already conducted some research. We do have some results on it, and we know that the robot will be trustworthy for humans in this way. So prospect of cognitive robotics, I mean, it has been ongoing for over 30 years. So its utilization is not only in industry, but also in healthcare, in homes, in smart vehicles, and so on. I could name, of course, a lot of examples of research, but I will just try to mention a few ones. And I will explain what we conducted within our group. So I think here it is seen that we are trying to create neural networks inspired by human brain. So it has to be neuro-realistic. I mean, it's not about making it the most efficient solution, but to acquire some features or characteristics which will mean in the future that we will kind of interact with robots and we will align with robots. And at the same time, the robots should have the experience with their physicality. So basically, not only explaining to the robot, yeah, here is a chair, here is a fork, here is a human. No, they need to perceive the environment or surrounding and somehow live it, let's call it, or embed it. This is very important for its possibility to adapt to different surroundings. So the interaction between robots and AI. So this was one of the main pillars. And we had this TERAIS project. We were trying to focus on building the technology and robots in such a way that they will be trustworthy, interpretable, and aware of humans. And this is a kind of a reminder or repeating what I have already mentioned. And we need to use, of course, via AI, we need to use interpretable AI methods in order to be able to implement them into our robotic systems.
I moved to the TERAS project part, and following by examples of our research outcomes, either in a human-robot interaction or robotics. In TERAS project, what we linked was the relationship between the human awareness or the robot awareness of the human, and this leads to trustworthiness. When we use the methods of explainable AI, we can encourage humans to trust robots because the robot can describe why they acted as they did, why they said or did what they did. At the same time, it's very important not to develop how the robot impacts the human, because we can also script it for research purposes, which means that we tell the robot the scenario exactly. We measure human reactions to the robot. We evaluate statistical results. But if we want to turn it to practice, if we want the robot to be intelligent, we want the behavior not to be prescribed. We want the robot to adapt to the situation, and we want the robot to trust the human, because it can happen that when the robot cannot evaluate what the human is doing, it cannot react correctly in a given situation. So we also did such research together with our partners, be it under the TERAIS project or will continue in explainable intelligence and robotics. We filed further applications with further partners. I will not spend too much time on this slide, but you can see the list of activities that can be done in such a big collaborative international project. So here you can see some pillars of our research, and what this chart shows is that each stakeholder in this international cooperation brought some domain knowledge, which was typical for each of the partners and which is dominant for each of the partners. So each of the partners, even though we were the ones who learned within that scheme, we were at the same time bringing our expertise and we were enriching each other. Therefore, these international collaborations are very important. They don't have to be international. You need collaborations at various levels. What was an important aspect from the research perspective was that we worked with two similar robotic platforms. This is Nick Robot, who is quite a cheap prototype developed by our partners in Hamburg, and this is ICAP. He's been in the market for some 20 years. It's the most exact assimilation to a human child, also in terms of behavior and also the degrees of freedom, how it can manipulate, interact, and how they are perceived by humans. It's probably the best representation. Then there are also other platforms that resemble people a lot, but you cannot do basic research with them because, for example, they don't have hands. They don't have hands similar to ours. They don't have such joints. They can just have two little degrees of freedom or not fine motorics. We have unitary robots with very detailed hands, but those don't have a face. So this is something that will need to be addressed. Why? I'll just add that it is important to have various platforms at various sites to be able to reproduce research, because this is something which is not considered so much, but the reproducibility of the research is key. Why I talked about how the robot looks and how they impact the human. When we do human-robot interaction, we check how persons perceive humans, how they adapt, and how we can exert an impact on the human so that the human takes the robot as their partner. It looks trivial, but it's not that trivial. It's very important to research this. And in this particular research, I'll just come to some showcase examples. We had a very important involvement with INT in Genova and with one institute in Japan and with other institutions. And when you can see this kind of slide, at the bottom there is a publication reference, and in this case we did this with those two platforms, Italians with ICAB and we with Nico, and we taught Nico to take a look at a human drawing and to redraw it, but also draw something for the human in such a way. And by doing this, we tested how the human would adapt their drawing to the robot. So the robot would first observe the human drawing something, and then the robot would redraw and turn it around. I think it's clear to people that it's not a child, it's a robot. And therefore, it is expected the robot would have some robot-like properties, but this is a depiction of what we had to do with the human drawings to achieve this trustworthiness that it's a robot, but at the same time they feel like a child. And what the result was that people really changed their style of drawing and behavior towards the robot, because the robot looked like a child, drew like a child, and they started doing their drawings bigger with more detail for the robots to be able to copy them. So this was one example of the cooperation or interaction between the human and the robot. What we then researched further, and we saw this was a big challenge and we would continue this research with other robotic platforms, was what we refer to as legibility of movement. If we want to have a robot who interact in our usual environment, and we want to expect what they do is meaningful. For example, if they are about to grasp an object, they would not lead their hand behind their head, but they would follow a certain trajectory, and so that's most user-friendly. It would be a ballistic trajectory as a human would do. Because I'm unable to explain it now in more detail, but the research shows that people have different strategies. I don't know if it's obvious or not, but the human body is a great machine compared to any other robot. Exactly. Like hand, rotational, joint, fingers, thumb. It's very difficult to do this with a robot to resemble human movement. So we focused on this, but then we at the same time observed how the robot observed the robot's movement. So how this robot movement is perceived by a human and how other signals are perceived. So here you can see various movement types, and here you can see our experiment where the robot was either looking at a point to be tapped on a big tablet in front of the robot, or it didn't look and it did the movement, but not completely. In this case, we can see a situation where just 80% of the movement is executed and the person has to show on the tablet where the robot's finger is pointing to. And it was shown. Again, an obvious but very important conclusion for further research. When the robot is looking and at the same time pointing, it's natural. And people have much better results in this situation. When the robot is looking away, it doesn't help that the robot does this movement in front of the person. The estimation where the finger is pointing would be worse than when they were looking. So that was quite an interesting finding. In cooperation with IIT Italy, we did automatic detection. Who was talking to whom? Here we have a triadic communication. Those two ladies are talking, the robot is observing, it learned to switch attention from one to the other, understand who is saying what to whom, and thanks to our systems based on artificial neural networks, the robot can understand that the two of them refocus their attention to a different person coming to the room. That's great. We need to develop this further. Our Nico robot is aware of the people in the room to a certain extent. A person comes in, he looks at the person, says hello. It was very interesting here that our colleagues Iveta Bečková and Štivo Pocoš, they got together with people at IIT because they were interns there, and they also did such nice research there. They worked on neural networks that they improved, and they also helped to improve this research. This is another example to illustrate our cognitive robotics. So the robot design, our Nico robot, has a hand with 4 fingers, doesn't have so many joints, so many degrees of freedom. So it's quite restricted to work with it. He cannot reach anywhere, but when we put an object to his personal space, thanks to AI, it is able to focus its attention on various objects. For example, here you can see that it can detect whether it's a duck, banana, onion, potato. Yes, it calls this potato because it cannot grasp firm objects. It can slide, but with other robots, we have higher ambitions. At the same time, yes, it looks, it chooses an object of its interest, it grasps it, and it can work with the object further. This is a diploma thesis in progress, not published yet. First, the student needs to hand it in. This was a very interesting problem. If we want a robot to behave in a certain way towards a human, they should be able to understand emotions from the human face. But work with data is a sensitive matter, so to find data to be used to train neural networks, because neural networks are very greedy in this respect, it's not that easy. So the entire diploma thesis of creating an emotion recognition system for a robot focused not only on how we put it into the robot and how the robot will then interact with humans or adapt to them in conversation, but it was also focused on what techniques to use to overcome the data problem, because freely available data contain 50% of happy people and the remaining part of the data are different emotions, like sad, upset. Try to imagine, a happy person is easy to recognize, even if we don't have a restricted data set. And we struggled with the fact that when, for example, here it's not very well to see, but I can read it for you. It's in English. On the left side, the child, in the data set, it's defined as angry. The neural network thinks it has fear. I would also think so, so we are struggling with it. And this gentleman is recognized as neutral or is defined as neutral, and the neural network thinks he is surprised. It could also be true. So what we started developing was that when we have insufficient data, which is good but not well represented in the dataset, the neural networks are doing mistakes because based on the data. So we came up with a technique that we would add attributes like glasses, hair color change, glasses change. We can also swap male and female face, and in this way we would keep this original emotion, but we would obtain more data and we would overall improve the performance, the success rate of the neural networks. I'm not quite used to giving presentations in Slovak sometimes. I just cannot find the right words in Slovak. This is another example of research that I've focused on since my doctoral thesis, and these are mirror neurons. In the brain, we have an apparatus that allows us to understand what we see. So those cells are in the motor cortex, but at the same time we see that they are also active when persons are just observing movement. They were found in apes just by accident, because they were monitoring the properties of these particular cells in the ape's brain, and later it was demonstrated they were also in the brains of humans, and they are mirror neurons because they mirror what persons observe. It can be movement that is observed, it can be an emotion, again located in a different part of the brain. So we focused on this movement and we said that, okay, if we want robots to understand, to really understand, not that we would preset, but really understand what the human was doing, we have to provide such a system of mirror neurons to the robot. I'm working on this research until now. There's a lot of work. We started with training the robot to do 3 kinds of some grasps, a concrete type of action, and we let the robot be observed by a different robot from various angles. And this is interesting in terms of science and interdisciplinary, not only from the perspective of cognitive robotics, but from the perspective of neuroscience and cognitive science, because this actual issue of how we translate what we are observing to our perspective, this can be tackled by the mirror neurons that have the same response whether I look at myself and when I do the movement, or whether I can see the person from the side, from the front, or from a different angle.
We continued in the research with our Nico robot. We continued. This is an example how one Nico observes the other one in a simulated area. Just remark on the side, we need to train the robots on simulators because, I mean, the robot, the traction and everything that is ongoing with the engines, I mean, this is not so good. It overheats the robot. I mean, it may sound really simple, but I need to explain it. So with the simulators, it is very important to mention that the robot has very different options to also do things that could kind of harm him, but they don't harm him because it is a simulated situation, and then the knowledge can be then transferred into physical area. So this is one field of research I have not been talking about until now because it has not been developed so far. But what we do know is that into the simulation, in the situation, we can also put the humans in this kind of simulated situation if we put it into VR. And this is then a safe interaction in virtual reality. I mean, humans with robots, and they don't harm each other. This is also something that we have been developing as part of our field of our research. Another area is very interesting. We used a cognitive small humanoid robot. We used one which has haptics, so he can touch. And he can touch, he has the touch, and what we investigated in this research, again, cognitive robotics, this is also connected to human cognition, and we modeled the situation, what happens with children in the womb when already a child or an embryo touches itself, and it's a correlation with what they are doing with the hand and what they feel. And this is an ability that is then further evolving. So maybe 7 months, or 6-7 months, a child or an embryo can basically react to stimulation, and my colleague has studied it on small kids and started to implement it then later on robots. And this was a very nice research we conducted, and this is again architecture, basically biologically inspired neural network model, and we wanted to teach the robot how to touch itself and basically understand its own body, understand how the body looks like. So these are the results. I don't have to comment on those so much, but this is one of the last points I want to go through. And this is my personal and also my favorite research. This is my second child. This is a so-called bio-inspired neural network, which is unique based on the fact what has been already researched, so it has some unique properties, and how it is architected is different from the neural networks in long learning and deep learning. And it's not super efficient, but at the same time, it has very interesting properties or features. What we have discovered is that when we connect the neural network in a way that it will observe everything with our cognitive, let's say, inspiration. And you would not expect the neural network to act. And this is, for example, the imagination, and you see these numbers or digits. These are the digits the robot imagines when we tell the robot, I mean, how does a number 1, 2, or 3 look like? And these are his own personal kind of images. It's not an average of the data it is learning, and the robot learns to create these images. It's not about telling him to learn it, but he was learning, or the robot was learning something else, was learning to name or describe the pictures. And this is a very interesting model, and it enables us to put it also into cognitive applications, either in this body scheme, in a way that the robots have this kind of possibility of imagination or imagining what they have already experienced and what they have been learning. So this is a different approach to how to work and create AI. I will conclude my presentation with the future perspectives, what we will be working on, or what we have been working on in our research group. Either it's some complex movements, by manual manipulation, orientation in space, communication with humans, and then also when the robot understands that, okay, now it's the human's turn to do something, then it's my turn. So turn taking up to this level, complex visual assessment of a scene and integration of a sensory motor, and then a behavior which is task-driven, and that the robot is aware that this task has been kind of conducted and is satisfied with the task execution, and then also understanding the context and also verbal, non-verbal context, and also emotion understanding. Thank you for your attention.
No, tak, v tej Trnave...
Wow. So in Trnava, we talked about Terminator, but now this week, I feel very good when I see that robots can already feel and imagine. But okay, let's open the discussion. You can ask questions via Slido or also personally, just raise your hand. So we have heard a lot and about the research, so I think the discussion could be interesting. So the first question already, if development of an AI robot from primary until maturing and to university education, should not the robot become independent and not only kind of evaluating or assessing orders critically? No, we are still at the elementary school, so no critical thinking, and also adults don't have critical thinking in many cases, so it's a long way to go, I would say. And as for imagination, before the next question pops up, this is something that is can also be deployed maybe in medicine for impaired people or for blind people. So, how can we replace maybe imagination, or how can we replace human eyes? I would not want to talk about something I would not be able to do. So no, this is some basic research, and diplomatically I would only tell you it could happen, but I don't know when. These things are really great. What about the next question? You can raise your hand if you have a question. Don't hesitate, and we can talk about the question and of course the answer. Everybody's hungry already? Okay. No, okay, we do have one. This is not my field of expertise, but maybe I work with digital twins, so I know the physical capabilities of a digital twins, and then it's not a problem to simulate these networks. I mean, 100% it is kind of real. It is or those interactions and physicalities. I know of a digital twin because, or I can create a database. I mean, why is it so difficult with you? Or let's speak about, for example, a robot doesn't have to be stand in balance, doesn't have to have balance, doesn't need a hand or a thumb, right? No. I mean, a simple answer to your question. As for our robot that we have been working with so far, we have restricted resources, and I will tell you the platform is, I mean, and we really put effort into it. I mean, this seemed to real. We didn't invest so much. The functional combination with the digital NIC and the physical NICO, but the robot doesn't run on many engines or robots. Motors, and it is our long-term objective for 15 years that, of course, this interaction, humans and robots in personal space, and that they work on something together with their hands. But unfortunately, the robot works perfectly in a simulator, but once you approach the robot, so the first experience was, yes, the hand starts moving, but the engine is heavy, and there is a divergency and so on, and the delta kind of grows. So it's a question of the platform. Now we have started working with this. I mean, we have received one from a grant with a new one, with this Uni 3 robot. It's a new type of robot. It's a better mechanical solution, and we think that this Seem to Real will be better with this Uni 3 robot. No, I mean, could you predict the delta? Unfortunately, in this specific robot, it was not possible. I mean, maybe the colleagues will be able to explain it better, these kind of technical details, personally or later. I mean, it could take quite long, and colleagues understand that it can take long. But the full group is here. We can discuss later, because there are so many technical details and practical technical problems connected to it that you can approach us later. Yes. And then, of course, at the lunch break and the next coffee break, serve for personal exchange. Next question. Is there something like animal-based robotics? So basically the robot on a child level is simpler than an adult one, and should not it be easier to work on it? And maybe the robot on an animal level will be even simpler. I would not claim that an animal is simpler than a robot. No, our perception of intelligence is very humanocentric, but also animals are very smart and intelligent. Not just because they cannot speak, it's not that they are not smart or intelligent. But to your question, before these small humanoid robots were developed, they were like the little dogs. Then, I mean, small humanoid robots, and the dogs have been using for therapeutic application. So also kids in kind of when they have to be isolated in hospitals, there's a better interaction with this kind of robots, and also children with autism interact better with robots, and so this is what robotics is also about. And then some material intelligence, let's imagine we could call it material intelligence. So robots copy, in a way, intelligent behaviors from the nature. So there is a robot that uses something like an octopus arm, or imitates or copies it. So basically the arm kind of flexes and can move on the water. So this is robots. Robots who interact with gravitation, robots who imitate a mouse or mice or some insects and so on. So I mean, I could go on this topic. Okay, so we have 1 year of this project ahead of us. So the next question. How far are we from an artificial AI human or robot with its own conscience? Well, conscience, it's a difficult question for cognitive neuroscience or science. How do I know that you have conscience? Do you have? Are you conscious? Human consciousness? I mean, well, I hope there are signs of it. Yeah, I could say that you have consciousness, and I could guess that all the people here in this room, or I can also think about my consciousness, and I can try to create a robot with artificial consciousness, but that's also a question of ethics. I mean, we want the robot to have something like a self-awareness or self-consciousness, so the robot, and this is what we are aiming for, that the robot doesn't only learn from like once we feed it with data and then it just does what it has to do, but we want the robot to learn and to acquire, but we are not at this stage. We need new methodologies of AI. We need new algorithms. We need the AI to learn from the interaction with humans and the environment, but in the long run. So we are creating these partial methodologies to this kind of artificial neural networks. And if we want the robot to be aware or to have a type of consciousness, we need to secure that, I mean, it's a long-term issue in order to be able to exist for the robot. I mean, what will be the first signal or sign of that the robot has consciousness? I mean, from cognitive neuroscience, we do have some methods. Like, for example, let's draw a point on your face and then look at the mirror. A cat, an ape, is able to identify itself and the dot on the face in the mirror. So we could create a robotic version of it. Then a very interesting concept in robotics is the Turing test, the so-called Turing test. So we are testing whether the robot can deceive the person, the humans, and convince the humans that it is not a robot. Okay, interesting. It reminds me of Asimov and his novels. And okay, now, okay, so the delta and simulation and so on, you can discuss during lunch this topic. I mean, yeah, just come by and we can discuss, or I can share some contact details of my colleagues. I work with informatics and I am a cognitive scientist, not a full expert on the robotics, but yeah, there are colleagues who could answer. Okay, in VR, will not the physical contact with robot be missing? And can you create a kind of a combination or interaction of humans? Yes, it is possible, and it will come. Thank you so much.
Za nás všetkých, že ďakujeme za skvelú.
Thank you for this great presentation and for your great work. And on behalf of Slovak Science and Slovakia, I mean, just pass my message that thank you and all the best for your next research. And we are looking forward to finding out where it will lead to. So once again, thank you, Kristina Malinovská, the Faculty of Mathematics, Informatics, and of the University of Comenius. So the first